some potentially important applications of the charged impurities in graphene, in the charged impurities in the form of artificial relativistic atoms. How is outlined like this? What I will present will be focused on some models for the study of ultra-relativistic and the quantum electrodynamic phenomena in all dimensions using graphene, which based on the fact that graphene can mimic some relativistic or ultra-relativistic physics. So, what is the motivation for this? What is the practical motivation for such study? Most of the high energy phenomena are studied in experiments using these very big devices, accelerators such as Large Hadron Collider, relativistic heavy ion collider, or FAIR facility in JSI, Germany, which are quite expensive, which are built using very big money and require rather big money for maintenance. And then the chance facility that appears in the context of graphene physics is the fact that most of these phenomena, or some of the phenomena, can be studied at tabletop level using graphene, where some of the ultra-relativistic phenomena can be realized in 2 dimensions. So, what we know from the condensed matter physics of last 10-12 years is the fact that some quantum materials such as graphene, carbon nanotubes, and some P-wave, D-wave superconductors can mimic relativistic physics or high energy phenomena. This includes also Dirac and Weil materials. And then, as to the graphene, the main issue here is that relativistic quasi-particles mimics ultra-relativistic behavior, despite the fact that the velocity 300 times smaller than the light speed. Also, the fabrication of graphene requires a lot of money, quite small amount of money, and graphene has a wide range of practical applications. And briefly, let me mention what is graphene. Graphene is a two-dimensional material which was studied first by several groups. Among the most advanced or successful was Manchester group with Andrei Gaim and Konstantin Niyazov. For the series of their studies of unusual properties of graphene, they got Nobel Prize in 2010. So the main physical properties of graphene, which make it attractive both from the viewpoint of physical fundamental and practical viewpoints, are its thickness, strongness, its lightweight, and the transparency, and so on. Also, another physical properties comes from the fact that quasi-particle has zero effective mass. Velocity of quasi-particles is much smaller than that of light speed, despite that the ultra-relativistic equations will be used to disguise them in so-called low energy regime. And most important maybe is Um, the coupling constant in graphene is 300 times smaller than that of fine structure constant, which appears in normal three-dimensional quantum electrodynamics. And also, the Kepler-Swan structure is possible, and linear dispatch relation is possible. All this make possible to test in graphene such high energy phenomena, such relativistic phenomena as vacuum polarization, finger propagation, Klein tunneling, Darmstadt effect, and other ones. So this, as I told, it is very thick monatomic material built up, made up from hexagonal lattice of carbon atoms, and it also can be considered as basic material for other nanomaterials like carbon nanotubes and fluorine. The part theory of graphene and the fact that the quasi-particles can be described in terms of relativistic Dirac equation can be, in terms of relativistic Dirac equation was established in 1947 by Wallace, and then some field theoretical model was developed, quantum-dynamical model was developed with divisions and melee, which allowed to some realized some theoretical studies which showed that its bed structure looks like this. And so the main fact, main fundamental fact for the graphene comes related to the properties of quasi-particles, which are described in terms of Dirac equation. This makes graphene completely different than usual materials, and since one of the reasons for that is the fact that in case of relativistic systems described by Dirac equation, there are four types of transitions from one quantum state to another one. Two of them, excitation and ionization, correspond or is similar to that we have in case of non-relativistic systems. Two more comes in the form of a production with capture and direct pay production. The pay production, if you consider behavior of relativistic system in external field, the interesting phenomenon which is called pair production or vacuum polarization, these are phenomena which are related to each other, occurs when the energy level reaches the boundary of the Dirac. If there is vacancy in the energy level, some electron from the Dirac can be captured, and the hole which appears in place of electron is interpreted as positron. And then what this implies that this kind of phenomena should be possible to be realized in graphene, especially if one uses so-called Coulomb impurities, which are simply artificial relativistic atoms in graphene. In that case, the very interesting phenomenon which requires in three-dimensional case, in normal case, using very expensive big devices, is the form of accelerators, can be realized at the tabletop level. So this color shrinking mechanism for pay production simply can be explained like this. If you have if your Dirac is perturbed by some external field. It can be optical or substatic Coulomb field. Then the ionization of electron from the C can occur, and this process is considered as the production of electron and positron pair. In case of graphene, it will be, of course, particle-quasi-particle pair production. If we will look at this process in case of Coulomb potential, which means that in case of simple atom, in the three-dimensional case, it looks like this. The lowest energy level of atom is given by this expression, where Z is 1 over 137, and if Z becomes higher than this value, 137, this energy becomes imaginary. And this feature was noted by Polytechnic and Smardinsky in 1945, who found that this is caused by the fact that in solving of the Dirac equation, charge is considered as point like object. But since charge in reality charge has some finite sizes, Polytechnic and Smardinsky resolved this problem by regularizing Coulomb potential. That means that they took into account the finite size of nuclei. And when the result of resolving shows that further inclusion of Coulomb charge leads to approaching of the energy ground-side energy level to the boundary of the Dirac, and where charging or embedding of Dirac by the level occurs at the charge at the charge 170. This is still not possible. Even nowadays, it's not possible to realize such a charge or nuclei symbols of such charge with such nuclei. Symbols of atoms of such nuclei. Polytechnic and Smardinsky, Polytechnic and Smardinsky suggested some other chemical realization of this high charge by suggesting that one should consider very slow collisions of two ions, two nuclei, whose total charge exceeds 170. And then after some critical distance, the electron starts to see this two charge as single one with the total value exceeding 170. And then according to that assumption, this pair production, string pair production should occur. But this still was not realized in the experiment because it requires two bare ions and they are very slow approaching to each other. So, which means that the effect was called Darmstadt effect because some people try to realize it in J-side in Darmstadt, but this experiment was not realized yet. And what graphene allows is to realize this process at table-top level without using any accelerator, just by considering two charged impurities. The three-dimensional version of this system was considered in our paper 1999, where we used some specific approach, and so let me explain how to do that. Before that, let me explain what are the charge impurities in graphene and artificial atoms in graphene. So if one bogus charge, Coulomb charge, Coulomb impurity in graphene, what will happen is it will capture electron. The electron in graphene becomes atom, where the electrodynamics is described in terms of two-dimensional Dirac equation. This system can be called artificial two-dimensional atom. Similarly, one can dope two impurities, then one obtains relativistic planar molecule, where the electrodynamics is also described in terms of two-dimensional Dirac equation with two centrifugal potential. So this one of the results I am going to present you in this talk is related to this system, which was considered. And another possibility is realizing electron dipole, relativistic electron dipole system in 2D by doping plus and minus charges. In that case, again, the dynamics of electron is described in terms of the planar Dirac equation with finite dipole potential. So, as for the atom, as for the relativistic planar atom, this was experimentally studied in 2013, and some by a group of, well, I think by the group of Eva Andre, if I'm not, or Andre Shikov, yes, by this group of South co-authors, and possibility of atomic collapse, which is also supercritical phenomenon, was shown in this study. And the molecular version has not yet been considered, but theoretically it was considered by our group in 2014, where we considered two-setter problem for in planar Dirac equation. And what we did was use some modification of the method for linear combination of atomic orbitals, relativistic modification, and studied computed the spectrum of the system and ground state energy level as a function of nuclear distance, and give some estimates for critical charge at which diving of the ground state level into the Dirac occurs, and that causes the particle and particle hole creation, or particle hole creation. And we also studied some transfer phenomena there. And then another problem we considered in the context of charged impurities in graphene was so-called electron dipole system, relativistic electron dipole system in two dimensions, where we also found some new effects, which I will show later. And this, unlike the previous two systems, planar atom or planar molecule, this system a bit exotic because this in 3D in normal situation it is impossible to create relativistic electron dipole system, because it will imply, for example, putting together some uranium nucleus and the anti-uranium nucleus, since the uranium nucleus cannot be synthesized. This was considered some exotic model. Actually, the model for this electron dipole system was proposed by our group, which was one of the tasks of my PhD study in 2099. And then according to the referees comment, this was quite exotic, unrealizable system. But at that time we agreed with the referee, but we did not know that after some 10 years or 8 years, graphene will be studied very well, and some possibility for realization even such exotic systems will appear. So this then what we did was in the context of study electrodynamic system in graphene was the Dirac equation, this finite electrodynamic potential, which was solved numerically and approximately analytically to have some density of states. I think we found also the local density of states of the system, which can be just observed by STM microscopy. And another thing we finding was very interesting effect, so-called effimov effect, which comes from the nuclear physics, was discovered first by Efimov in 1970, which implies some exponential scaling of energy, different energy levels. What we found by analytical calculations in this relativistic electron dipole system was similar scaling, which allows us to say about the existence of manifestation of Efimov effect in relativistic electron dipole system. So this was second finding of our study. Of course, we computed energy spectrum, energy terms, and we explored the possibility of supercritical phenomena such as electron hole pair creation. This was another thing which is under study now is possibility for realization of one-dimensional relativistic atom in graphene as by doping charged impurity not in the big graphene sheet but in so-called graphene nanoribbon. If the width of the ribbon is small enough, the electron motion will be one-dimensional or quasi-one-dimensional. In that case, we need to describe it in terms of one-dimensional Dirac equation with one-dimensional Coulomb potential, which actually can be solved almost analytically to obtain a spectrum energy levels, which can be found from this so-called circular equation where these W are the Wiener functions, and some results for the energy level at different channels and time, which are presented in this table. And what is interesting is estimating critical charge, critical value of the charge, which causes creation of electron-positron phase. This can be considered this can be done by considering this Coulomb potential, utilize the Coulomb potential, taking into account the finite size of the one-dimensional nucleus, and again, one can derive some circular equation, solving which one can obtain the value of the critical charge, which can be presented for some lowest energy states on this slide. So summarizing, what I presented is some discussion for potential application of graphene as a testing device for some high energy phenomena, ultra-characteristic high energy phenomena, where so-called supercritical effects such as electron pair creation and polarization can be experimentally observed. And this can be done by logging charge impurities into graphene, and then one needs just to estimate this critical charge, which then can be experimentally observed. Of course, some other experimental observed characteristics such as local basis of states and energy spectrum can be defined. And the last thing is consideration of relativistic electron dipole system, where we found FEM effects. And what can be then, what could be then studied in the future is so-called quantum chaos phenomenon in relativistic system using the artificial relativistic atmosphere graphene and quantum localization, which this is also a phenomenon related to quantum chaos, which is some analog of Anderson localization, and relativistic atoms in Harvard space just by considering Harvard version, change the impurities in Harvard space, Harvard graphene. So this work was supported by the joint grant of Dirac. This activity, some part of this activity, Dirac presented to be used UZBEKISTAN grant. Thank you.
I'm not an expert, but you emphasized emphasis almost like kind of applied aspect, but in the talk actually you now emphasize also fundamental aspects, because this is almost an ideal system where you can go from basically you have a quantum and a relativistic, which is fantastic. Yes. On this matter. So it looked to me that the options are phenomenal if you want to expand on that.
Yes, actually it looks like practical, but it is in fact fundamental, because fundamental from the viewpoint that some very fundamental high energy phenomena such as electron particle pair creation or vacuum polarization or Klein tunneling can be experimentally studied using the graphene, due to the fact that graphene or particles in graphene mimic some relativistic behavior, high quantum dynamic or even relativistic behavior. Of course, this is true not only for graphene, but today it is possible to have to experiment realization of other relativistic particles like Matrasulov-Turin, where again, as a condensed matter mimic. These are not real relativistic particles, but these are quasi-particles that mimic relativistic behavior.
Black hole analogy in your system.
Yes, actually, there are some activity, some potential for the potential meaning of black hole behavior in graphene. But I'm not familiar so much. But I know that some people work on meaning of black hole behavior by considering some these different curvatures, curved graphene versions. When you have this, you need to describe this. Yes, strained graphene, ending or strain. In addition, when you strain graphene, or bend graphene, besides this mimic of strong gravitation, another phenomenon occurs which is called pseudomagnetic field. In strained graphene, some pseudomagnetic field appears. It's not real magnetic field, of course. We, unfortunately, we are not working on band structure calculations now, but I mean, we are working, we have some publication on band structure calculations, but not for the case of twisted graphene. So this is twisted, electronic twisted systems are relatively new area, and some people did a lot of progress there, like some people like Vladimir Popov, for example.
Can you again for your presentation and thank you for your